So when you think of coordinates, what do you see? What do you picture? What's in your mind's eye when you hear the word coordinates? Points, okay. So a point like 0, 0 or something like that. So given that we sort of picture points and coordinates as being interchangeable, why is there anything to say in the section on coordinates with respect to a basis and changes of coordinates? How come we can spend an entire day talking about this if coordinates and points are just two different sides of the same coin? Where do coordinates come from? Maybe is a deeper question.
X and Y values.
X and Y values. That's initially where we see coordinates. So if I just, poke on a different point here in this coordinate system, that point right there, that point, at least according to the app where I just clicked here, has coordinates 5, 4.5. But why? Where do these numbers come from? This x here, this x value, and this y value. What are those x and y values really? What do they represent in our diagram? Where does that 5 come from? Like, how would I know if I wanted to say for sure that this point had the coordinates 5, 4.5? Well, on the one hand, yeah, but having a slope that agrees with the slope of this doesn't necessarily tell us that our point is 5, 4.5, because this line would also have the same slope. This line would have the same slope. That line might have the same slope, and so on. So where did that 5 and that 4.5 come from an elementary standpoint? Go all the way back to when you first learned about the XY coordinate system. Right. So what are we measuring? We're measuring a distance along the x-axis, and we're measuring a distance along the y-axis. And those two distances are the coordinates of our point. 5 and 4.5, and then we have this sort of picture where we're connecting them up like that. So what I like to think of is that coordinates come from graph paper, in a sense. That we can determine the coordinates of a point if we happen to have that point plotted on some graph paper. Then all I have to do is count the squares. If I want to know what the coordinates of this marked point is, I'm going to start from the origin, and then I'm going to count over 1, 2, 3, 4, 5 squares. And then I'm going to count upwards 1, 2, 3, 4 and a half squares. And then I get the coordinates of my point. I think in a lot of Algebra 1 classrooms or whatever, that might be how they're teaching people to navigate the XY coordinate system. And we're going to hang on to that idea, even when our coordinate system happens to change. That it's still what coordinates tell you, the coordinates of a point, is just how to count on graph paper. 5, 4.5 has those coordinates because I'm counting 5 in the x direction and 4.5 squares in the y direction. But the graph paper, too, has to come from somewhere. Usually it comes from a place like the Quartet Publishing Company in Skokie, Illinois, or whatever, right, where they produce your graph paper. But when they produce your graph paper, what are they doing? I used to live in Skokie, so I had to get a plug in there. Where is that graph paper coming from? Well, to produce graph paper, we have to know how wide each square should be and how tall each square should be. And each of those, from a linear algebra perspective now, we can describe each of those with a vector. For instance, I might describe the horizontal width of my graph paper using a vector like 1, 0.
So each box is equal to a vector?
Yeah, I'm thinking of each box as having its length and its width described by a vector, where maybe the width here is described by the vector 1, 0, and the height described by the vector 0, 1. And that is a very convenient choice. It's an incredibly convenient choice. It's so convenient, in fact, that we call that choice the standard choice, the standard basis. By the way, let's take a pause here and remember what basis means. First of all, this is a standard basis of what? Of what vector space? It's kind of an answer to the question, where can I get to by taking linear combinations of 1, 0 and 0, 1? The easier question is, where can't I get to? I can get anywhere in the xy plane through linear combinations of 1, 0 and 0, 1. So this is a standard basis of the entire xy plane, R2. But again, thinking back to last week, why is it a basis? What are the two criteria that make a basis a basis? Yeah, the first one is it has to span. It has to span all of whatever set it is a basis for. So in this case, it spans all of R2. In other words, every point in R2 can be written as a linear combination of 1, 0 and 0, 1. In particular, it can be written, let's say I have the point 5, comma 4.5. How do I write that point as a linear combination of 1, 0 and 0, 1? Well, I can just write it as 5 times 1, 0 plus 4.5 times 0, 1. Gives me that point. So any point in R2 we can write as a linear combination of these standard basis vectors. And it's pretty clear by inspection how we would do that. We just take the x-coordinate, we put it in front of 1, 0. We take the y-coordinate, we put it in front of 0, 1. And that's all there is to it. And that's what makes them, by the way, the so-called x and y coordinates. Let me write that in this little sidebar off here. That what we think of as the x-coordinate of a point and the y-coordinate of a point, when we use these terms, these just mean coordinates with respect to the standard basis. In other words, coordinates if our graph paper is created by the vectors 1, 0 and 0, 1. So that's the first requirement, that it be a basis, is that it has to span all of R2. We have to be able to get anywhere in R2 through linear combinations of these vectors. But what else do we have to know in order that this is a basis, 1, 0 and 0, 1? What's the second requirement? Recall that a basis is a minimal spanning set. In other words, it's a set of vectors that spans whatever vector space we're trying to span, but it does so with as few vectors as necessary. And when it does so with as few examples as necessary, that means that there is one and only one expression of each point in R2 in this example with respect to this basis as a linear combination of these basis elements, which means there is a unique solution to the vector equation linear combination of this basis is equal to some point like 5, 4.5. And if there's a unique solution to the vector equation, then what do those vectors have to be? Linearly independent. There we go. So that's the second thing we require of our basis, is it needs to span the entirety of the vector space we're trying to span, and that set has to be linearly independent. Because only when that set is linearly independent can we be guaranteed a unique solution. And it's a unique solution to the equation, let's say, C1 times, in our example, 1, 0, plus C2 times 0, 1 is equal to some point A comma B, or X comma Y, let's call it. And when there's a unique solution, that solution is called the coordinates of the point xy. So there's the connection. That the coordinates of a point with respect to a basis is just the solution of the vector equation C1 times the first basis vector plus C2 times the second basis vector gives us our point. So the coordinates are the solution of this vector equation. And only when our vectors, our set of vectors, are linearly independent will that solution be unique. Because if we don't have uniqueness of solutions, we're not going to have uniqueness of coordinates, and we don't want that. Right? We don't want to represent a single point by an infinitude of different coordinates. We want every point to have only one representation in coordinates with respect to a given basis.
So you plan independent unique coordinates and unique solutions.
Yes. Yep. Uniqueness of solutions to this vector equation, which, because these solutions are called the coordinates of our points, implies unique coordinates with respect to a basis, which is what we want. So that's the set of definitions. Let's back up from that and look at some specific examples that hopefully will illustrate what exactly is going on. When I choose a different basis, I get a different graph paper, and when I have different graph paper, I have different coordinates. So let's suppose that instead of 1, 0, and 0, 1, let's suppose that instead of 1, 0, and 0, 1, we decide to play around with this a little bit. Let's take our graph squares and make them not squares anymore. Let's extend it out to here. So let's make our basis, instead of 1, 0, and 0, 1, let's make it 2, 0, and 0, 1. So that's my new basis. 2, 0, and 0, 1. And having a new basis, so those vectors are here and here now. Having a new basis gives me different looking graph paper. And so that point, which in standard coordinates was 5, 4.5, this is standard coordinates, now in my new basis has new coordinates. But the same procedure. If I want to figure out the coordinates of this point, I should just count graph paper squares, which aren't squares anymore, but rectangles. But the process is still the same. If I'm starting at the origin, then to get to this point, I'm going to count over 1, 2, except only 2.5 squares this time. And then, vertically, 1, 2, 3, 4.5. I'm still counting 4.5 squares up. So the coordinates of this point, with respect to our new basis, so I'm going to call this basis something. I'm going to call it a script letter B, the way that is done in the textbook. But the coordinates of this point with respect to that basis now are 2.5, 4.5. And so in the book, when it's written like that, we'll write it as a column vector and then a little b underneath it. So those are the coordinates with respect to our basis 2, 0, 0, 1 of the point, which in standard coordinates is 5, 4.5. And the reason that it works that way is because if I take these coordinates, 2.5, 4.5, and I form that linear combination of my basis vectors, 2, 0, 0, 1, I take that linear combination, sure enough, I get 2.5 times 2, and then 4.5 times 1. So that's what I mean when I say that the coordinates are really just a solution to the equation what times 2, 0 plus what times 0, 1 gives us 5, 4.5. So now we've determined the coordinates of this point in a different basis. And how did we determine it? We determined it by, in principle anyway, in principle we would have determined it by solving this vector equation. C1, the first coordinate, times the first basis vector, plus C2, the second coordinate, times the second basis vector, is equal to our vector, 5, 4.5, our point. So really, the coordinates were determined, C1, C2, are defined by the very idea that they are a solution to C1 times times 2, 0 in this example. C1 times 2, 0 plus C2 times 0, 1, which we can represent that linear combination by this matrix product, is equal to, then here I have what I want, 5, 4.5. So this tells us how linear algebra can help us discover the coordinates. Because we know, based on linear algebra, how to solve this vector equation, and the solution of this vector equation is equal to the coordinates of the point 5, 4.5, with respect to the basis b. So I'll call them the b coordinates of 5, 4.5. And to find them, all I have to do is solve this system of equations. And that determines the b coordinates. So that means I can ask the question about this linear equation, questions we know how to answer. For instance, how do I know that this equation even has a solution? How do I know that we can actually find coordinates for, say, the point 5, 4.5? Why is it consistent? What can we say about this matrix that will tell us that this is always a consistent system of equations? Let's make it an augmented matrix here. So I would have this 5, 4.5. Uh-oh. Just move it over by hand, I guess. 5, 4.5. So how do I know that this system is going to be consistent? I have 2 pivots. In fact, all it takes to solve this system is divide the first row by 2. Easiest row reduction we've done in a while. But no matter how we do solve this system, we can tell right away it has 2 pivots. And because there's a pivot in every row, we can say for sure that this is a consistent system. In other words, I can find the coordinates, not just of the point 5, 4.5, but no matter what was over here on the right-hand side, let's call it x, y, I could find the coordinates of any point I wanted to, because this system is always consistent because there's a pivot in every row. So that's how we know we have a solution. And by the way, that's the part that tells us that my vectors, in fact, span all of R2. Because this equation is always consistent. I can write any x, y as a linear combination of 2, 0, and 0, 1. Now, how do I know that those solutions are unique? In other words, how do I know that when I find these coordinates that I have one and only one answer? There's no free variables because there's a pivot in every column. And again, that is a manifestation of the linear independence of this set of vectors. So whenever I have a basis of all of R2 or R3 or whatever it is, when I put those basis vectors into a square matrix, that square matrix will have a pivot in every row, and so we can use it to determine the coordinates of any point in Rn. And there's a pivot in every column, meaning that when I find the coordinates of any point in Rn with respect to that basis, those coordinates are unique because of the linear independence of our set of vectors in the basis.